Hi, I'm Harsha Marela and my project partner is Chakra Zatota. We are working on Kaggle team project. Our dataset is Home Depot. First, we begin the project by importing the important libraries needed for the project. Then we load all the datasets provided in the Kaggle competition, through which we can check the dimensions of train data, which has instances 74,067 and a test data which has instances 112067. After that, we briefly take out the descriptions of whatever data is provided to us, as you can see here. We join the product description with training and testing individually. We do a left join and we use the key as product ID. Later on we check NaN values, and from checking that we get training data which has 207 rows of NaN values and test data which has 319 rows of NaN values. We replace NaN values by replacing them with empty strings, and once they are replaced you can see the NaN values are 0. After this step we do the tokenization. In the tokenization we use the following variables. The first variable stores the description and keys of each token. The next token df is used to store the document frequency of tokens. The next is the product length, which is used to store the length of the product. The token association variable stores the association of each token with the others. Then we have a term frequency token. Now what we do is we remove stop words by tokenizing the content. We remove all the stop words necessary and apply porter stemmer for doing the stemming operation. In the loop behind, we update and calculate document frequency, the term frequency, and then they calculate the term association. Later, we calculate the IDF values based on token DF, which were already calculated in the above loop. Then we calculate the product length, and we get product length with token TFDF values as weights. Here we return whatever we wanted to calculate, and we are calling the functions and getting tokens for product titles and description. Now I will pass on.
Coming to the query expansion, we want to expand the queries using the mutual information, word net, and the correlation association matrix. And first I want to explain the mutual information. Based on the tokens association values we got from the get tokens information function, we are finding the frequency of the term X and term Y, and here we are calculating the the tokens mutual information, and in this function clearly we can see that because I am implementing the basic formula of it. And here we are expanding the queries using the mutual information we calculated above. And first we can see we are calculating the tokens mutual by calling this function compute mutual info, and then we are expanding the queries, and here we can see that I'm expanding the queries using the titles, with respect to the tokens of the title and also with respect to the tokens of the description. Here we are expanding the queries, and here we are computing the mutual information. And the thing I want to say here is, in the query expansion I am adding 2 tokens for each token in the query. And coming to the word net here, and the same, I'm adding 2 tokens, and before that I'm getting the synonym sets here for each query word. And if the word is not equal, if the synonym is not equal to the word, then the synonym will be added to the query. Like if the query word is the table, and if the synonym set has the table, it won't be added. And if it is a reading table, definitely, it is clearly distinct with the table, right? So that's why it will add to the query. And here I'm expanding the queries using WordNet. And coming to the correlation association matrix, first I want to create the document term matrix here. And before that I want document term matrix by taking the products as rows and the terms or tokens as the columns. And by taking the inverse of the document frequency and multiplying it with the document term matrix which we define here, we will get the association matrix. And based on the the correlation matrix, and based on the correlation values, the top two terms with the high correlation values will be added to the query, and it will be done with for every query term. And yeah, here we are expanding the query here. After computing the correlation matrix, we are expanding the queries. And before that, I want to say one more thing. Um, the tokens calculated for the with respect to the titles has the length 12820, so we can able to create the document term matrix. But when it comes to the description, it is more than 1 lakh. So I'm getting some memory issues, so that's why I'm not expanding the queries with respect to the description with the description tokens.
Yeah. In the next step, we feature engineering. All we are doing is whatever data we have obtained above, we are using it to calculate different similarities and coefficients, namely cosine, dot, dice, jacquard, and even other important features have been calculated here. As you can see, we have been just calculating cosine here, dot product here, and dice coefficients, and then we return all the similarity features here. Next will be explained by Chakri.
In the future engineering, I want to add one more point to my friend's explanation. The thing is, in addition with the similarity features, we want to add the statistical features here, like the common words ratio, common words query, like that. The reason for that is all the similarity measures is highly dependent on dot product. So if the dot product is 0, all of the similarity values will be 0. So which will lead to, high correlation between them, which will eventually lead to the overfitting of the model. So in order to overcome that, I just want to add the statistical terms. And after that, we are getting the features for raw data. Raw data means we didn't expand the query, and we just gave the in its normal form. So that's why I called it as raw data. And in the mutual info, with the queries expanded with the mutual information, I got the features here, and the expanded queries using WordNet, and the features with the expanded queries using correlated words. And after getting the features for train data, I got the values for test data. I got the features for the test data in the same way, and I'm storing everything in the CSV files. When it comes to the training the machine learning models, I'm using the random forest, nearest neighbor, gradient descent, and ridge regression. The main idea behind that is I just want to find the optimal parameters for each model, and based on that I want to check the test RMSE values of each model, and out of that I want to pick the best one which has the least test RMSE, and I just want to do ensembling method so that I can able to decrease the test RMSE. And here I'm combining all the features except the WordNet, because the WordNet is adding more statistically relevant terms, so that's why I'm skipping that. Apart from that, I'm adding every features. So here we can see I have done the the hyperparameter tuning, and based on that I got the values here for this gradient descent, reach, and the nearest neighbor. And out of that we got the good scores for the random forest, so that's why I'm picking the random forest, because it has the least test RMSE at 53097. I just want to improve that, so that's why I'm doing ensembling method for finding the optimal number of estimators. And here we did that, and here we can see it here. So at 13 we can see that clearly it is an optimal parameter, and based on that we did here, and we are got the final test predictions, and the and that's why we are submitting. I mean, that's all. We are submitting this one. Thank you.